In our very first section, we're looking at sample spaces and probability. We're going through a lot of the basics of probability today. Lots of basic stuff, so lots of definitions, lots of little rules. And then next few sections, we get into doing some of the more complex things with probability. So probability in general is the chance of an event happening or occurring, however you want to phrase that. So some areas where you might have maybe seen probabilities used or heard of them being used. Games of chance, such as card games, slot machines, lotteries, things like that. You might have heard the chance of winning the lottery or the probability of winning at a certain type of card game or certain hands of poker. Maybe you've heard of those things before. Some of those things we will get into. Probability is used in insurance to help figure out insurance rates. What's the probability that a particular person might suffer a heart attack, or what's the probability a certain person might get cancer, and a lot of that's based on your family history and things. Weather forecasting is definitely based off probabilities. And it's also, we looked in our very first unit, we talked about inferential statistics, and we're going to spend a lot of time there in our second trimester, but probability is the basis for our inferential statistics that we'll look at more second try. So basic concepts, here we go. If you're talking about a probability experiment, it's a chance process that leads to well-defined results. And those results are called outcomes. So an outcome, just to get a little more specific with it, an outcome is the result of a single trial of a probability experiment. So if you're talking about an outcome, it's the result of one trial. So whether you're talking a trial of flipping a coin, rolling a die, whatever you happen to be doing for your experiment, an outcome is the result of a single trial. An event consists of one or more outcomes. So an event can be any subset of our sample space. We're going to talk about sample space in just a second. So an event could consist of just one outcome, or it could be two or more outcomes. If you just have one outcome, you have a simple event, and we're going to get into lots of examples today. Compound event is when you have two or more outcomes. So if for events we're looking at subsets of our sample space, we need to figure out what the heck a sample space is. Sample space is simply all your possible outcomes when you are doing a probability experiment. So what are all the possible things that could happen? What are all possible things that could be outcomes? And then all I have in the table there for you would be the experiment. And again, just keeping it basic. Today is the basics. We'll get into more than just, yep, we're going to flip a coin or roll a die. But if you toss one coin, the possible outcomes, or I could flip a head or a tail. So my sample space, I have to list both of those possibilities. So your sample space is just simply all your possible outcomes. If you roll one die, your possible outcomes are the numbers 1 through 6. Answering a true-false question, your possible outcomes are true or false. You toss two coins, there's your possible outcomes. They could both be heads, both be tails. First one heads, second one tails. First one tails, second one heads. So those are just all the possibilities for those basic experiments. And then I just put a little note on there. This is already on your sheet for you. On page 187, so if you need to find it, I don't want to go through the work to create the sample space for rolling two dice with all its 36 outcomes. And I don't want to take the time to have to try to draw out the 52 cards from the deck of cards. But you will have questions about those in your practice and things. So that's where you can find the sample space for those two things. I don't want to take for granted that all of you are thoroughly aware of everything that's in a deck of cards. Some people are big card players, some people aren't. So if you have card questions, you can check out page 187 if you need it. Big question I always get, so Miss Golly, how do we write probabilities? Typically a probability is written as a fraction when possible, a simplified fraction when possible. That's the ideal. Decimal if you need to. Sometimes just given the results that you have or given the information that you have, decimals are really your only option. Percentages, you want to try to use them, probably not as often. There are going to be appropriate times where you use percentages, and we'll get into that a little more as we get further along with probability. So how do I write my probabilities? Those are our options. How do I round them? The rounding rules, I left those on your sheet, so you have that as a resource, and so you don't have to try to dig back through the reading. Again, you should use reduced fractions. Simplify those fractions. There is that handy feature on your calculator that will turn decimals back into fractions, and it has them simplified for you. If you're not sure how to do that, as you practice, let me know. Round to 3 decimal places if you're doing a decimal. If it's a really small value, round to the first non-zero digit. So if I have, we talked about rounding to 3 decimal places, well, but what if the first 5 of them, and this would be a very, very small probability, but what if the first 5 happen to be zeros? I don't want to just round off and say 0, because if you say the probability of something happening is 0, you're saying there's no chance at all it's going to happen. If I have even a 0.50564 chance of something happening, there's still a chance that it can happen. Very small, but there's still a chance. So I can't just round to 0. So you would want to round this. You would keep all your zeros, and then you'd round it to a 6. So that's what we mean by the first non-digit, the first non-zero digit, not the first non-digit, first non-zero digit after the decimal point. We will not necessarily in this chapter, in our next chapter, we're going to be using tables in Appendix A. Just use the number given. So when you're using tables in the textbook, and that will happen in actually our next few chapters, just use the number that you're given in the table. Sometimes when you're dealing with an experiment, it's hard to just think of the sample space right off the top of your head. Tossing a coin, that's easy. It's heads or tails. Rolling one die, that's easy. Numbers 1 through 6. But now if we have something like tossing 3 coins, I know for some of you, you would sit there and be like, well, yeah, I can list those out. When you're tossing 3 coins, you might not be sure how many outcomes you should have. You might not be sure what they should all be. You need to make sure you don't repeat anything. So one way for us to get our sample space when we're unsure of what it should be is using what's called a tree diagram. So if we're tossing 3 coins, what we need to think about for each event, start our little tree here. The first thing I'm doing is I'm looking at all the possible outcomes for coin 1, or whatever your first event is. And it might not always just start with 2 branches. If the first thing I'm doing is rolling a die, I'm going to have 6 branches to start. So take a look at what your first event is. My first event, I'm going to have, well, 1 coin out of the 3. Possible outcomes on coin 1, I could get heads, or I could get tails. It's a possibility for coin 1. Now, after coin 1 lands heads or tails, now we have to look at coin number 2. Coin number 2 could then land heads or tails, could land heads, could land tails. So you're coming up with, again, all the possibilities. We don't know what coin 1's going to do. It could be heads or tails. If coin 1 lands heads, coin 2 still has the possibility of being heads or tails. If coin 1 lands tails, coin 2 still has the possibility of being heads or tails. Then we need our third coin, and that third coin could go heads or tails. Third coin could go heads or tails. So now you might be thinking, okay, Miss Guy, so how does this give me my sample space? The tree diagram is going to ensure that you don't miss a case. I know for some of you are thinking, Miss God, I could go through and I could name these off. I could list these off now that I know what you mean by tossing 3 coins. But you might end up missing one. The tree diagram, if I count the end branches, there's 1, 2, 3, 4, 5, 6, 7, 8. So I should have 8 possibilities in my sample space. So my first possibility, we follow the branches. Let me grab my highlighter here. So my first possibility is going to be that they all come up heads. That's my first possibility, is that they are all heads. So we're going to list head, head, head. My next possibility, we're just following the branches. Coin 1 heads, coin 2 heads, and then coin 3. My highlighter doesn't, there we go, and coin 3 being tails. So you work your way through the branches until you've hit the end of every branch. So we're going to have head, head, tail. So just take a minute and see if you can finish off the other 6 possibilities. So again, that tree diagram is just helping us ensure that we get all the unique possible outcomes. We don't have any repeats in there, and that we don't miss one. I know for some you're thinking, oh, that's kind of a pain to have to draw that out versus just trying to list them. But sometimes just trying to list them can take longer, and you might miss a case. You might miss a possible outcome. So tree diagrams can be very helpful in that regard. So now getting into actual probability, we're just going to hit a couple basic types today. The first type is called classical. What classical probability does, it assumes all outcomes in the sample space are equally likely to happen. So they all have an equal chance of happening. So if I roll a die, each of those 6 numbers has an equal chance that it's going to land on that number. Or if I flip a coin, heads and tails both have an equal chance that they're going to come up. The big key with classical probability is also known as theoretical probability. It's in theory. I don't actually flip the coin. I don't actually roll the die. In theory, here's what should happen based on the information in my sample space. You don't actually do the experiment. You just go based on your sample space. In theory, here's what should happen when I flip a coin, or if I roll a die, or if I draw a card out of the deck. To find classical probability or theoretical, I just want us to start getting used to a little bit of the notation. The probability for any event, we symbolize with capital E. So P of E, this notation right here, I don't have that at the bottom, this means the probability of an event, and whatever that event is. So that's the probability of an event. Am I going to want you to use that notation? Yes. And we'll continue showing what that means as we get into actually doing some of the probabilities. So in the numerator, we just have the number of outcomes for your specific event. So how many times or how many ways can your event happen? And then the N of S is the number of outcomes in your sample space. So how many times does your event happen over the total number of possibilities? That's what you're looking at for this kind of probability. So let's try this out. We have 3 coins are tossed, and we already have the sample space for that on our tree diagram. This should be right above your example on your handout. Find the probability of getting 2 tails. So when we write our notation, we have probability, and you can just put, you could write 2 tails if you want, you could put 2 t's, you could put probability TT, whatever you'd like. What event are you looking for? What event are you finding the probability of? That's what replaces the E in the parentheses. So it's not just going to be P with a capital E every time. You're going to replace the E with the event you're looking for. So probability of 2 t's. So take a look in your sample space we created. Again, it's right above here on the handout. We did the tree diagram. How many of those 8 outcomes have 2 t's? So now the debate becomes, well, Miss Golly, is it exactly 2 t's, or does there just need to be 2 t's? If it doesn't say exactly, it just needs to have 2 t's. So how many have 2 t's? So do I get to include the one with 3? Yeah, I do. Because it doesn't say exactly 2, it just says it has to have 2. So how many have 2?
4.
So 4 of them have 2 t's. Out of how many total possibilities? Out of 8. The ideal way to write a probability, again, is as a simplified fraction. Now, here's where we get into the at most and the at least. How many, so probability, at least 1, and you can just abbreviate tail with T is fine. So take a look through. When we're talking at least, is 1 the most I can have, or is 1 the fewest? 1 is the fewest. At least 1 means 1 or more. If you need to make a note to yourself, you can. This is 1 or more. So look through your sample space. I don't have mine up on the screen, so I got to take your word for it. How many of our outcomes, how many out of the 8 have 1 or more tails? 7 out of the 8. And I can't simplify that any further. Now, at most 1. At most 1 means what? It's the most I can have. So this is 1 or less. So take a look. How many in your sample space have 1 or less? So we're talking about 0 or 1. How many have 0 or 1 t's? Do you guys agree? Is it 4? I don't have the sample space in front of me. Yes? So be very careful with the at most and the at least. I know sometimes when we see at most, we're thinking, oh, we want more than that, but we don't. At most means that's the most I can have. At least that's the fewest I can have. If it says exactly, you can have no more or less. So just be careful with some of the wording. That's what can trip people up with probabilities. Now, if you're not very familiar with a deck of cards, again, page 187 has that for you. If I put card questions on the test, I will supply you with a copy of that sample space from your book. I will. I don't think it's fair if you're not that familiar with the deck of cards that you get a probability wrong. I don't see the point in that. All right, so if we're dealing with a deck of cards, we want to find, and actually I'll go ahead and give you guys a couple minutes just to play around with this one. I'm just going to jot these down up here so you can check as you go.
Yeah.
Face cards, folks, literally have to have a face on them, so only Jack, Queen, King.
But wait, why is... Okay, 2.
rhymes. So go ahead, check yours with mine. Again, face cards have to have an actual face on them.
Yeah.
There we go. Now check yours with mine. Got it. So continuing with our basics, here's some basic probability rules. These are definitely good things to know as you're doing some of your calculations. The probability of an event, and again, we just use capital E for generic for event when we don't know specifically what it is. The probability of an event, it can be 0, it can be 1, and it can be anything in between. So if you think about it in terms of probabilities can be written as percents, if you think of it, a probability can range anywhere from 0 to and including 100%. You can't have more than a 100% chance that something's going to happen. And you can't have less than a 0% chance that something's going to happen. So I can't have, there's a negative 0.27 probability that it's going to not rain today. I can't do that. Okay, there's no negative probabilities. They can't have a negative chance something happens. And there can't be more than a 100% chance that something will happen. And then there's just everything in between. So, 0, probability of 0 means it's not happening. There's no way it's going to happen. If it absolutely will happen, the probability is 1. And again, you can think of it in terms of percents if that makes it easier for you. I think most of you probably, when you hear probabilities, you probably hear mostly percents, even though that's usually the less preferable way to write them. And if you add together all the probabilities in your sample space, it will equal 1. So for example, if you add them all together, so if we roll, let's say we roll 1 die, single die. Your possible outcomes are 1, 2, 3, 4, 5, and 6. The probability that I roll a 1 is a 6th, plus the probability I roll a 2, roll a 3, roll a 4, 5, and 6. This also helps us illustrate, too, equally likely. Each event in that sample space has a 1 out of 6 chance, a 1/6 chance that it's going to happen. If I add together each of those individual probabilities, my total is going to be 1. If I add together each of the individual probabilities, it's going to equal 1. And again, this is for our theoretical probability with our sample space. If we talk about the complement of an event, now that we're getting a little more familiar with events, we found some classical probabilities, talked about some of the basic rules. The complement is the set of outcomes in your sample space that are not part of your event, whatever that happens to be. And we will do several examples of this. So basically, your event is going to include so many outcomes in your sample space. The complement will be the outcomes that are not included. So your event is going to consist of so many outcomes in your sample space. The complement is the outcomes that are not part of your event. How we show we're using the complement of an event instead of the event itself, you just put a bar over the capital E. Or when we were doing the probability of getting an ace, we would have just put a bar right over the A we did for ace. Or when we were trying to find a face card, we would just put a bar over face card. So again, remember, you have to fill in the E with whatever you're actually trying to find. Some of the rules, and some of these can provide some shortcuts for us. Let me go through piece by piece. I know all three pop up at the same time. I apologize. This is probability of our complement, the bar over it means the complement, equals 1 minus the probability of our event. Remember, if we add up all the individual probabilities in our sample space, the total is 1. So if I want to find the complement of an event, I can do 1 minus the probability of that event. Same thing works the other way. The probability of an event is 1 minus the probability of the event's complement. Again, we just saw we add together all the probabilities in my sample space, it totals 1. So if I know the probability of my event and I want to find my complement, I just take it away from 1. The last one, if you add together the probability of an event and its complement, that takes care of all your outcomes in your sample space, so your total should be 1. You add together all the probabilities for each event in your sample space, or each outcome in your sample space, I should say. Your total is 1. That's a very important thing to keep in mind for us. So let's get a little more specific on what complements are and how to find their probabilities. Let's talk complement first. So if we want to find if the event is rolling a die and we get a 3, okay? So if my event is getting a 3, if my event is rolling a 3, and I'm not talking probabilities yet, we'll do the probabilities. If my event is a 3, what would the complement be? The complement would be everything that's not a 3. So the complement would be 1, 2, 4, 5, and 6. It's all of the other possible outcomes. So if my event is rolling a 3, the complement is every other possible outcome. So every number except 3. So if we want the probability that we roll a 3, we know that there's 1 3 out of 6 numbers on the die. If I want the complement of that, we just put a bar over it, and we can use one of our rules. It's simpler for me to find the probability of a 3 than trying to figure out 1, 2, 3, 4, 5, 6. So I can do 1 minus the probability of getting a 3. Or if you want to list these out and get the 5 out of 6, you can. It's totally up to you. So the complement is all of the other outcomes in that sample space. All the other ones you're not using. So if you flip 2 coins, and we did do the sample space of 2 coins. I know it's on the other side of your sheet. So here's the sample space. They could both be heads, both be tails, head, tail, tail, head. Those are the outcomes when you flip 2 coins. So if my event is 2 heads, the complement of that is all the leftovers. So if my event is 2 heads, the complement of that is getting rid of that and writing everything else. So it'd be 2 T's, head, tail, tail, head. So those 3 outcomes would be what my complement would be. So if we talk probability, the probability of getting both heads is 1 out of 4. The probability of the complement, and remember we just denote that with the bar, would be 1 minus that 1 out of 4. Or I know you're thinking, do I have to do that 1 minus thing? Or if I know based on this that there's 3 outcomes, can I just jump right to the 3 out of 4? Yeah, you sure can. But sometimes when you're asked to find the complement, if you have a larger sample space, sometimes it's easier to find the probability of the event and subtract it from 1 than to try to figure out the probability for the complement without finding the event itself. So just be careful. These are very small sample spaces, so finding the probability of the complement, it's not too tough, it's not too time consuming. But if you have a bigger sample space, sometimes finding the probability of the event itself and subtracting from 1 will be quicker. And you're just going to have to judge that as you come across each problem situation, what's going to work best for you. So I want to give you guys a chance to try out the third one if you haven't already. I know some of you work ahead of me, and that's all right. Try it. Now, there's nothing wrong with having to jot down what the sample space is. I know we're all very familiar with the days of the week, but if you need that visual, and sometimes working with probabilities, we need that visual to see how many outcomes are in our event and how many total outcomes are there. Sometimes it just helps to see it. So our event is day of the week, beginning with T, complement, day of the week, beginning not T. All right, so the probability we get a T would be 2 out of our 7. So probability of not starting with a T, you can do 1 minus 2/7, or however you came up with 5/7 is okay. Again, I don't want these ugly decimals. I don't want us rounding when we can do something as simple as 5/7. Okay, that's what I'll be looking for. We looked at classical, aka theoretical probability earlier, where we didn't have to actually do the experiment. It's just based on our sample space. Now, empirical probability, it's based on observations. So empirical probability, you have to actually perform the experiment. So it's no longer just in theory, here's what should happen. It's I did the experiment, here's the results. Here's my probabilities based on my results. So with our formula, the two formulas they're very similar. In this case, though, we have to look at is how many times does our specific event happen. So I'm actually going to roll the die and see how many times do I get a 3 out of how many times I actually roll the die. So N could also be, for better phrasing, it's your number of trials. So instead of sum of frequencies, you could also say N's just simply your number of trials. How many times did you roll the die? How many times did you flip the coin? Those types of things. So the little example I have down at the bottom, a coin is tossed 60 times. Heads occurred 43. So the probability of heads, and yes, get used to the notation. Will I expect the notation? Yes. So get used to it, please. Practice with it. So the probability of actually tossing heads, it's no longer 1/2. It's based on my experiment. It's 43/60. So in theory, if I flip a coin, I should get heads half of the time. In theory. Now, if I actually flip the coin, here's my results. My probability is 43 out of 60. That's the difference between the two. Theoretical is all in theory based on my sample space. Here's what should happen. Empirical, I actually do the experiment. Now, to give us a little bit different look, I have one here for you. To give us a little bit different look, we're not flipping a coin, we're not rolling a die. We're looking at some information collected from a men's clothing store and what was purchased. One of the easiest things, and I know it's easy to hunt through the question, but just an idea for you, you can set up one of our little frequency tables that we've made. You can have color and you can have frequency. Sometimes it just helps. Am I going to make you make a table? No, I won't. But for myself personally, when I'm trying to find probabilities, it's much easier for me to have all the facts listed out with the frequencies right by them than to try to keep hunting back through the question. So the colors, we have blue, we had 12. Green was 8. Gray was 4. And we have black at 7. Your total frequency, that's going to be very helpful. We're not told how many shoppers there were. So we do have to find our total. And that's one of the things sometimes people miss out on. Like, okay, Miss Galley, so I know a blue sweater, 12 people bought them, but wait, how do I make that a fraction? Sometimes you're not specifically given the total. So sometimes you do have to just go ahead and add your frequencies. So go ahead, guys. All right, so probability, blue sweater. Now make sure you're careful though, we've got blue and black, so when you're doing your notation, make sure you're somehow distinguishing. Blue and black are both BL, so you might need to actually put the word. So probability, we get a blue sweater, was 12 out of 31. Probability, gray or green. Gray or green, we end up with 12 again. Neither are green nor black. Now here's where, and I think some of you earlier like, do we have to find the complement? Here's where you could. So you could add the green and black together and take it from 1 if you want. So 1 minus, if I put green and black together, what do I get? 15. Green, black is 15. So we end up with 16 out of 31. A sweater that was not black, there's a great chance for the complement. And here's a great example of where using the complement is easier. For me, it's easier to do 1 minus. It's easier in this situation to do 1 minus. It's easier to do a 1 minus the probability of black instead of having to add together the green, the gray, and the blue. So it's quicker for me to do 1 minus the probability of black than to add together all the 3 other ones. So just a couple places where you could do the complement and could make things faster. Law of large numbers. I'm just going to sum it up here. Make sure that you do read the section, and that's part of what I ask you to do for the assignment. As your number of trials increases, your empirical probability, so what you get from actually doing the experiment, will approach your theoretical probability. So we had before that we tossed a coin and we got so many heads out of 60. We weren't at a half. But as we increase our number of trials, when we flip the coin, we will get closer and closer to the 1/2 that in theory we should get. So the more and more trials we do, the closer that empirical probability gets to the theoretical. Please make sure that you read the section. And then the practice problems. I know for some of you, you're thinking, okay, Miss Galley, I got this classical and empirical stuff. How many times does it happen out of the total? I've got that. The thing I definitely want to make sure And I have it written on your sheet, this last chunk of questions. Make sure you get to those because those are the ones that are having you create tree diagrams and find your own sample spaces. They're not the ones where, oh, it's rolling 2 dice and I can just look on page 187. They're not just a deck of cards. So please make sure you at least get to those questions. It's not a ton. They should go quick. The 2 through 12, 13 to 33, they should go quick for you.